Consider this picture of a baseball player. Even though we only see a flat, two-dimensional image, we can easily infer the player's 3D pose. We can also imagine his 3D poses as he swings his bat in the split second before and after the snapshot. We can do this because we have a mental model of 3D human dynamics that we develop by observing many people in motion. In this work, we present a computational model that can similarly learn a representation of 3D human dynamics from video. At test time, from a video input, our model outputs temporally consistent 3D predictions. And from a single image, we can predict not only the current 3D mesh, but also how the 3D poses change in the surrounding moments. Here is an overview of our model. Given a sequence of images, we first extract per image features. We then train a temporal encoder that learns a representation of 3D human dynamics over the temporal window centered at each frame. This temporal representation, capital Phi, serves as a feature encoding for a small movie strip, from which we can predict the current 3D human mesh. We also predict the past and future 3D poses for this frame, which encourages the model to pay more attention to temporal cues and the dynamics of the person. Our approach can be trained with various types of supervision. When available, we use 3D ground truth. Otherwise, we train only with 2D reprojection loss, which measures how well the recovered 3D mesh and camera project onto the ground truth 2D pose annotations. We also use an adversarial prior to constrain the 3D meshes on the manifold of real humans. To transfer the dynamics to a static image, we jointly train a hallucinator that takes a single image feature and tries to hallucinate the movie strip representation. We also pass the output of the hallucinator to each regressor to ensure that we can still recover 3D humans and their dynamics. A major challenge in predicting 3D humans from images or videos is the lack of data. Videos with 3D ground truth annotations are often recorded in motion capture environments that do not reflect the complexity of the real world. While our approach can be trained with ground truth 2D poses, existing video datasets in the wild are limited in quantity. However, millions of videos are uploaded to the internet every day. In this work, we harvest this potentially unlimited data source by training our model with pseudo-ground truth labels obtained from running OpenPose on unlabeled videos. We curate a new dataset, Vlog People, with 2D pseudo-ground truth annotations. Vlog People contains significantly more video content than existing video datasets with 2D ground truth annotations. We also introduce a second new dataset, InstaVariety, with 2D pseudo-ground truth annotations. We scrape to videos from Instagram using 84 hashtags that cover a wide range of activities. Together, our new pseudo-ground truth datasets are 2 orders of magnitude larger than existing 2D datasets. We find that training on our new datasets reduces 3D error by 4% and improves 2D pose accuracy by 6%. Please refer to the paper for a summary of the results. Now, let's take a look at some examples in which our network hallucinates motion from a single image. Here, we see a single frame of a basketball player. Our model predicts the 3D pose as well as the poses in the surrounding moments. We can compare this to the actual images 5 frames in the past and future. Since our model makes 3D predictions, we can view the meshes from a different angle. Here, the model learns to perform a wind-up and follow-through for the pitch. Here, the model correctly predicts that the tennis player is tossing the ball into the air. Here, the model follows through the tennis serve with a visible weight shift. Clearly, predicting dynamics is a challenging problem. From a single image alone, many motions are ambiguous. For example, here it's unclear whether she is going to move her arms up or down from a single input frame. In such cases, our model learns to predict constant pose. Not only can motion be ambiguous, but the pose from a single image can also be uncertain. This produces poor dynamics predictions, which are initialized from the current pose estimate. Note that incorporating temporal context resolves these ambiguities. Now we demonstrate our results on video input. We first compare our method with a single view approach. The pink mesh is the output of HMR, a method that only uses a single frame. The blue mesh is the output of our method, which incorporates temporal context. Our method, the alternate viewpoint, highlights the improvement in temporal consistency. Here, we show some of our failure modes. 3D prediction is challenging when there is occlusion. For example, here the person is occluded by the banner. Person-to-person occlusions can also be challenging. For certain types of occlusions, such as when the legs are covered by a table, our model can still predict reasonable 3D meshes. However, fast motion and extreme poses remain difficult. Here are more results on the test set from InstaVariety.